side into Mesoporous support. Okay. And I would like to give you a very general or broad introduction. So the last speaker mentioned that there are many porous materials, right? Numerous porous materials. And according to the classification, we would have very small nanoporous materials called microporous materials with the pore size less than 2 nanometers. And larger than 50 nanometer would be microporous. And in between, which we are very interested in, is the mesoporous materials with pore size between 2 and 50 nanometers. And here, when I talk about the mesoporous materials, I am more focused on order the mesoporous materials because we use self-assembly or use non-confining synthesis to get this kind of ordered mesopore. And there is a very famous saying here that the space may be the final frontier in our society. And this is true for our universe, right? How the stars move around and how they interact with one another and how they move around the orbiters. And this is also true in the community of mesoporous materials that we would like to explore the nanospace. So in the nanospace, we may confine different molecules or even some like some large molecules, proteins, or even nanoparticles in this kind of nanospace. And also we would like to control the wall of this nanospace. That means the atoms or molecules define these nanopores. So we would like to control this kind of property because this kind of nanospace may have very special physical chemical properties as well as applications in catalysis, adsorption, and some other areas. And today I would like to focus on carbon materials. I think in the last 2 days and also today we already know about many carbon materials, and there are many stars, right? Like graphene, carbon nanotube. There are carbon stars in previous years, and but like graphene, although the surface area, the theoretical one is very high, it's around 2,600 square meters per gram. But in reality, it's very difficult to get such high surface area. One reason that is because we are very difficult to get monolayer carbon, and also in reality the layers may be aggregate or may be stuck together, and in reality we may get several hundred square meters per gram. And also in such kind of planar structure, if we load the nanoparticles in this kind of support, the nanoparticles may be easier to detach or rapidly detach from the support. So this is why we are more interested in porous carbon materials, because these nanopores may be better to disposing and stabilizing nanoparticles. And also these nanoporous carbon materials, they have also have similar good chemical thermostability as well as other electrochemical properties. And also we can get very high surface area. In reality, for example, mesoporous carbon materials, we can get around 3,000 square meters per gram at the moment. And also very large pore volumes, which is not the case for like graphene or carbon nanotubes. And they have very wide applications for mesoporous carbon materials, for example, separation, catalysis, energy storage, and conversion. But of course, because carbon itself is inert, right? It's basically inert. And if we would like to use them for separation or catalysis, we need to introduce some functionality into the pore surface. So that's why we would like to load some nanoparticles in this kind of carbon materials. And recently there are many research boxes in carbon materials. I think this is a summary of what we are doing in this area. The first one is many people are interested in control the porosity. And nowadays the symmetry, I think, is very mature. We can get a lot of symmetries, but here the size, hierarchy, and the pore orientation or gradient is very popular or very hot research area to control, especially the get hierarchical mesopore, micropore materials with designed orientation and pore gradients from inside to outside. And of course, second one is to control the crystallinity of the carbon walls. Especially in electrochemistry, we would like to get higher crystallinity. And the surface, as I said, the carbon is inert, so people have done many nice works to introduce functional group into carbon surface, like graphene as well as carbon nanotube. Many functional group can be loaded, can be introduced in the surface. And here the red one is what I would like to talk about today. So we try to load some nanoclusters and nanoparticles in this kind of Mesoporous carbon materials, as well as I will talk a little bit about the particle engineering part. So how to get the different large micro-size microspheres, and how to make these microspheres in relative large amounts. So I will talk about this part. So first, let's have a little bit of history about the Mesoporous carbon. As I said, we are focused on the ordered Mesoporous carbon, right? So in history, the first time that such kind of Mesoporous carbon is reported is dated back to 1999. So theoretically, it's very easy, right? Very easy. We got a template or a mold, very simple mold, and then we can load some organic precursors into the nanospace of this mold. Of course, there is many different cases. So depending on the interaction between the pore and the carbon precursor, normally this is adhesive forces, right? Adhesive forces. And then if the force is very strong, we may coat a layer on the surface of the nanospace. And if we can also completely fill this nanospace. So in these two cases, we may get a like this one, a nanopipe or nanotube arrange. And in this case, we may get this kind of a nanowire arrange. So there are many research work that to control the template itself, as well as to adjust the precursor to control the interaction between the template and the precursor to get different structural materials. And also this kind of replica that from this one can be further repeat this process to get this kind of, we call it positive replica. So this is a little bit history. And from this kind of scheme, we can easily think about that we can, when we loaded the precursor, we can add some meta, right? Add some meta or add some other species together with carbon precursor, so that we can get nanoparticles loaded in the carbon products in one step. So very simple. There are many very nice research work about this. So what I did is just some simple examples shown here. The first example is about Mesoporous platinum adgraphic carbon nanocatalyst. So this, I didn't show the background here, but the purpose for this catalyst is to synthesize some nanocatalyst for oxygen reduction reaction, because platinum is a very common catalyst for oxygen reduction reaction. But commercial catalyst, platinum is easily to aggregate it or easily get oswald rapidly during cycling. So here we just use this kind of template method to get this kind of very stable catalyst. The advantage is very stable. I will emphasize again later. So we got a template, right? Template. Then we just use wet impregnation. Use wet impregnation to load a little bit of platinum precursor into the nanochannels of these templates. And then we use a CVD method with methane as a precursor, because methane is a precursor for growth of graphene, right? Growth of graphene, so that we can get higher crystalline carbon materials. And then we can control the time, temperature, and also the amount of this one to load this kind of to growth carbon, and simultaneously reduce this kind of precursor to metallic platinum. And after remove this kind of template, we can get this one. That's the platinum nanoparticles is embedded in this carbon nanowire. And of course, carbon is always more or less microporous with very many small pores. So it's accessible to very small molecules like oxygen, hydrogen, but it's not accessible to like methanol or some other molecules. So this feature get to make this catalyst highly stable, and but the activity may be not so high as compared to noble meta-based nanostructures. So here is some structures. So if the loading of platinum is lower, basically if it's lower than 5%, then we can see that the nanoparticles is embedded in the carbon walls. But of course, if the loading amount is very high, the part of the nanoparticles we are located outside the nanowires, not like this case, almost that embedded in the carbon walls. And here I just maybe I will not go into details. So we use it as an electric catalyst for oxygen reduction, and we get high activity, especially the stability. So if we talk about stability here, we control the commercial catalyst with our catalyst this is after 5,000 cycling, because in our catalyst, the nanoparticles is embedded in carbon walls, so it's very stable. After 5,000 cycles, we can see there are not severe aggregation or agglomeration, but in the commercial ones, we can see that previously it's even smaller than these nanoparticles, but after cycling, there will be transfer and detached from some areas, and they are aggregated in some areas. This is common issue in commercial platinum catalyst. So this is one advantage of our catalyst. So this is one example. And next one is also about the platinum nanoparticles. So in this case, we have, I think we have a good design that to get some kind of platinum encapsulated in graphene nanoboxes. So here we use zeolite A as a template, because zeolite A have very small pore size, right? Methane cannot go inside the very small nanopores. So if we use ion exchange to input platinum ions inside this very small nanopores, and then we use CVD with methane as a carbon source, because methane is not accessible inside this kind of very tiny nanopores. Then we can only deposit graphic carbon layers outside this kind of nanoboxes, and then we after carbonization at high temperature, and then remove template, we will get this kind of graphene nanobox encapsulate this kind of ultra small platinum nanoparticles. Here are some results here. So we can see that this kind of cube morphology of graphene nanobox, and inside we can see that very small platinum nanoparticles, about 1 to 2 nanometers. And we found this is even higher active for oxygen reduction reaction. As you see here, it's much better than commercial platinum catalyst. The activity or the calorie density, I'm going to look into details here. Here I just show how we get this kind of nano-catalyst. So here we just show 2 examples about CVD, and next we will give you another example that use a solvent-free method to get this kind of also oxygen reduction catalyst. Here again, we still use this kind of mold, and without any solvent, we just mix the Mesoporous silica templates, iron nitride and ammonium acid, histidine, mix it together, solid mix it together, and then after grounding a little bit, and then heat the mixture, and then because the amino acid, histidine, and this one will form complex like this one, complex, and then during the heating, because of the capillary forces, the melted liquid will be trapped into this kind of nanochannels, and then we do carbonization and remove the template. We will get a very nice electric catalyst that have both iron carbide nanoclusters of about 1 nanometers, and also we will have this kind of atomic size. Both of them, this one and this one, are reported to be highly active for oxygen reduction reaction. So here is some results. Here we can see that from the TEM and dark field TEM, we can see that there are very small, tiny nanoparticles or nanoclusters embedded in this kind of carbon particles. And from these results, we can see that this nanoclusters is basically it's iron carbide. It's not iron oxide or metallic iron, because we first use this kind of synchrotron XRD and also synchrotron near-edge fine structures to define this kind of functionality. So from here, we can see that this is 0 valence of iron. This is 2 plus iron. That can be allocated to this kind of iron carbide and this kind of iron nitrogen atomic size. So we use this kind of a catalyst for oxygen reduction reaction. We are not going into details because, as I said, I just introduced the methods. But we use this as an electric catalyst for oxygen reduction. We found that it's very active and extremely stable in both alkali and acidic conditions. This is very competitive results if we compare the literature results. And also this kind of electric catalyst is methane tolerance. We can see that if we use commercial catalyst, if we introduce methane to the system, then we will have an electrical response. But our catalyst shows no tolerance to this kind of methanol. And also after cycling, after many 5,000 cycling, you can still see that the iron carbon nanoclusters and maybe the atomic side will still highly dispersed in these carbon molecules. Okay, this is 3 examples about we use this kind of hard templating, or we use the mold to load the nanoparticles inside the carbon molecules. Here I will introduce another method because from history, as I said, we have the previous method to get the Mesoporous carbon materials. And another method is developed in about 12 years ago that use self-assembly to get the Mesoporous carbon materials. This is in my previous supervisor's group. So we use self-assembly with this kind of surfactant, amphiphilic surfactant, and this kind of phenolic resin as a carbon precursor. And because this kind of hydrogen bonding between the surfactant and the phenolic resin, that we are organized together. And we use evaporation-induced method because with evaporation solvent we can get different muscles, and muscles can be organized to different structures, for example, hexagonal structure and also cubic structures. So this is a very general and versatile method. And so after this is reported, we also think about to load nanoparticles inside this kind of nanoporous materials for catalytic applications. I will just show you one example here. So here we have a good design that to get a nanoparticle loaded Mesoporous carbon materials. Here we choose a template. This is a carbon template, and use post-loading method. So in this template, it's very special. We have 2 Mesopore. One is about 5.6 nanometer, and one is located in the wall of the carbon, about 2.3 nanometers. And when we do synthesize some catalyst, here in this case is iron oxide, because iron is a versatile catalyst. And in previous method, people normally use wet impregnation to load the iron nitride into the support and then direct carbonization, heating the mixture. And in that case, the precursor may be aggregate, transform or grow to very large aggregated nanoparticles. But here we just add one simple step to overcome this issue. So in this case, we just after loading the iron nitride in the precursor in the template, we just use the ammonia to hydrolyze the metal nitride to metal hydroxide, because metal nitride has a very low melting point. So during heating, it's very easy to aggregate, and so that you get very large nanoparticles. But metal hydroxide or like iron hydroxide, they have very higher melting point, so they cannot easily transfer or aggregate together, and then we can get a very smaller size and very well disposed iron oxide nanoparticles in the carbon. And they are basically side selective loaded into the large Mesopores and then leave the smaller ones empty. That is accessible to substrates for catalytic or adsorption catalysis applications. So here's some results. So here, the loading amount is about 40%. In this case, 40% is a very high amount, and we can see that they maybe not very clear. So this is a calcination, different calcination temperature, and we can get different size of iron oxide nanoparticles. From this kind of TM image, we can see that this kind of the black dots uniformly dispersed in the whole Mesoporous support, right? And I will not talk about the applications because time limits. So finally, I will talk an example about particle processing. Because previously, when we talk about synthesized Mesoporous materials, normally we use the hard templating. Hard templating is very time-consuming, and people say it's very costly. And the soft templating is cheaper, but in reality, people the synthesized amount is small, and we hope that to develop some method to scale up for scalable synthesis of this kind of Mesoporous carbon based materials. And also this is from the perspective of particle engineering aspect, because when we look at carbon materials, people may focus on nano-size range, but in real applications, especially in catalysis, especially in fixed bed or fluidized bed, maybe large micro-sized spheres is preferred. And if you look at literature, there are many methods about this kind of micro-sized spherical nanoparticles use this kind of aerosol spray drying pyrolysis to get this kind of nanospheres. But they're basically very small, maybe from tens of nanometers to a few micrometers. So in our group, we have a background of use spray drying to get this kind of nice uniform microspheres. And our purpose is that we would like to integrate some chemical concepts, especially self-assembly, and with this kind of spray drying technology to get some functional nanoparticles. So like here from a liquid droplets, then with this kind of spray drying, one single step to get this kind of functional nanoparticles. And we control the formula of the precursor, then we can control the nano-functionality of the final microspheres. And we'll talk about one example. And here, as I said, that when we synthesize this kind of Mesoporous materials, we have used the soft temperate method, right? And here in order to integrate this kind of the self-assembly in the spray drying, so we use the soft template method. And here we need to have two issues to overcome. The first one, if we would like to get microspheres, the liquid droplets, like this droplet, may deform. Because if the droplet is very large, the droplet after drying may deform or may change its shape. So this is an issue. And this depends on the capillary forces and the electrostatic forces. For example, here is some example. If the electrostatic forces of the molecules inside the liquid droplet is smaller than the capillary forces. Capillary forces means that during drying, there will be a gaseous product coming out from the liquid droplet, and then there will be capillary forces. And then we will get this kind of cramped or D-shaped microspheres. And fortunately, in our case, this kind of phenolic resin and the surfactant have very strong interactions with electrostatic forces. So the droplets will maintain its shape. But there is another issue where we try to get this kind of microspheres is the surface thickness, because both of this surfactant and this phenolic resin, they have very lower glass transition temperature. So they're very sticky. That means very sticky. If we use spray drying to get this kind of microsphere, they will be very sticky and it's not possible to collect them. So this is a very difficult issue to overcome. And so we will just show you them how we get this fixed. And the first example is that we use this kind of formation of surface ridged crust or surface shells to stabilize the droplets. That means we have a liquid droplet, right? Liquid droplets. And in the droplet we have the surfactant, and then we have the phenolic resin. Then we add some silica source, TUL silica source. And during the drying of the droplets in those microparticles, then we use a temperature of about 160. And then we have some kind of temperature gradient. The surface of the droplet will have a high temperature. And that means in the surface, the silica source will hydrolyze faster, very faster, and to form a surface crust, silicon crust. And this silicon crust have a higher glassy transition temperature. That means it collects very well individual microspheres, like this one. And the inside is hollow. We are not going into the mechanism. And we get this kind of microspheres. Then we do carbonization and remove the silica template. Then we will get carbon microspheres like this, right? So very uniform microspheres like these ones. And if we look at the surface area, it can be up to about 2,000 square meters per gram. Pore volume is about 1.7. And also this kind of microspheres is hollow inside. Of course, we get solid microspheres. So we can also control the size. Simply control the solid content and the drying temperature will get different size of microspheres. Okay, finally I will introduce the nanoparticle loading about this kind of nanoparticles. So here in this case we use the surface crust, right? Surface crust to stabilize the droplets. And another method to stabilize is just using coordination chemistry. Because the resin, the phenolic resin is very sticky. Then we add some metal ions. metal ions will coordinate with this kind of phenolic resin, and then the glass transition temperature will enhanced, and then we can get very nice microspheres. So like this. So we get these microspheres here. And very nicely, we can control both the macro size of the microspheres as well as nanoparticle size of the metal inside. For example, if we input iron or cobalt or some other metals. And this, how we this achieved is that if we would like to control the overall macro size of these spheres, we just control the metal ion to the phenolic resin mass ratio. We can control the size as well as to control either hollow or solid. And then we similarly control the solute content. So we have liquid droplets. We can control the concentration of the solid to get a different size and also either hollow or solid microspheres as shown here. And there's another range. If we introduce, for example, iron nitride or cobalt nitride, we can add some other ligand, or we similarly control the drying temperature, because higher drying temperature, then faster nucleation. Faster nucleation means smaller size, and then we can get a very small nanoparticle size down from maybe 2 to 3, 2 nanometers to about 30 nanometers. We can control this kind of nanoparticles, like iron, cobalt, something like that. This is just some example here. So this is we can control out macro size, and the inside we have this nice nanoparticle loaded in the Mesoporous carbon particles. So this is just an example. So I think I will end my talk. So through this talk, hopefully I'll just show you some methods that we can use this simple method to load metal nanoparticles into Mesoporous carbon materials. And we can may have some valuable method to control the size and location, or as well as the overall size of the microparticles. And also we are doing some research about the application of these microspheres in catalysis and adsorption. Okay, finally, I would like to thank my collaborators, especially my previous supervisors, and also some fundings from the Natural Science Foundation of China and some companies. And also thanks to my students for their hard work. Thank you very much for your attention.